Hey everyone and welcome. Today we're going to crack open the universe's ultimate rulebook. We're talking about thermodynamics. Yep, the laws that dictate how energy works everywhere and in everything, from your morning coffee to the most distant stars. So let's just dive right in.
So think about this for a second. You've seen it a million times, right? A hot cup of tea cools off. But have you ever seen a lukewarm cup of tea suddenly start boiling all by itself? Of course not. But why? Why does it only go one way? Well, the answer is way deeper than just common sense. It's fundamental physics, and it's all laid out in the laws of thermodynamics.
All right, our first stop is a little weird. It's called the zeroth law. And yeah, they actually came up with it after the first and second laws. But it's so basic, so foundational, they had to stick it right at the beginning. This is the law that even lets us talk about temperature in a meaningful way.
The zeroth law is actually beautiful in its simplicity. All it says is this: if System A is the same temperature as System C, and System B is also the same temperature as System C, well then A and B must be the same temperature as each other. It's basically the if A equals C and B equals C, then A equals B rule you learned in math class, but for heat. And that simple idea is what makes thermometers possible.
The key phrase here is thermal equilibrium. It sounds fancy, but all it means is that heat has stopped moving back and forth because everything's reached the same temperature. Think about it. When you use a thermometer, you're waiting for it to reach thermal equilibrium with your body. Once it does, you know the temperature of the thermometer is the same as your temperature. That's the zeroth law in action.
Okay, next up, the first law of thermodynamics. You can think of this one as the universe's strictest accountant. The rule is simple and non-negotiable. You cannot create energy and you cannot destroy it. You can only move it around or change its form. That's it.
But before we get to the famous equation, we need to get one concept down: internal energy, which we represent with the letter U. This is all the energy a system has just sitting there. It's the energy from all its tiny molecules jiggling, vibrating, and buzzing around. It's like the system's own private energy bank account.
And here it is, the law in all its glory. Now don't let the letters scare you. This is one of the most powerful and important equations in all of physics. It's basically an energy balance sheet that works for absolutely everything in the universe. It tells us exactly where every single bit of energy goes.
So let's break down this balance sheet. Delta Q is the heat you add to the system. Let's say you're heating up some gas in a cylinder with a piston. Now, that energy has to go somewhere, right? Well, it has two options. It can either increase the internal energy, the delta U. That means making the gas molecules move faster, which we feel is a temperature increase. Or the system can use that energy to do work, the delta W, like the expanding gas pushing the piston up. The point is, the energy you put in is always perfectly accounted for. Not one bit is ever lost.
So if the first law says you can't win, you can't just create free energy, the second law is even tougher. It says you can't even break even. This is the law that puts a direction on everything. It's the reason for the arrow of time. It explains why heat flows from hot to cold, and why your room gets messy all by itself.
The second law usually gets explained in two main ways that sound different but are really just two sides of the same coin. The Kelvin-Planck statement says you can't build a perfect engine that converts heat into work with 100% efficiency. There's always some waste. And the Clausius statement says heat will never ever flow on its own from a cold thing to a hot thing.
So what does this all mean in plain English? It means that every time energy moves or changes form, the universe gets a little bit more disorderly. This cosmic trend towards disorder has a name: entropy. Entropy is always increasing. That's why your coffee cools down, the heat spreads out, creating more disorder. And it's why every engine has an exhaust. There's an unavoidable tax of waste heat in every single energy transaction.
Okay, so to really use these powerful laws, we need to learn to speak the language of thermodynamics. And that means understanding the critical difference between the state of a system and the process that gets it from one state to another. So, the condition of a system at any specific moment is described by its state variables. You know these, things like pressure, volume, and temperature. Think of them like the GPS coordinates for the system. They tell you exactly where it is and what its condition is right now, and they don't care at all about how it got there. And this table just illustrates that difference perfectly. State variables are about the destination, but other things, like heat and work, are path-dependent. The amount of heat you add or work you do depends entirely on the journey you took to get from state A to state B. So state variables are the destination, heat and work describe the route you took.
Now, physicists have this little trick they use to make their calculations easier. It's an idealized idea called a quasi-static process. Just imagine a change happening so unbelievably slowly, so gradually, that the system is always perfectly in balance with its surroundings. Now, nothing in the real world is this perfect, of course, but this theoretical tool is absolutely essential for figuring out things like the maximum possible efficiency of an engine.
So we've covered the big laws and the language we use to talk about them. Let's pull it all together now and look at the handy toolkit of formulas we've picked up along the way.
These are the heavy hitters right here. We've got the first law, that's our energy accountant, the ideal gas law, PV equals mu RT, which connects a gas's pressure, volume, and temperature all in one neat package. Then we have the Carnot efficiency. This is huge. It tells you the absolute theoretical speed limit for how efficient any engine can be. And finally, the formula for an adiabatic process, where no heat gets in or out. Super important for understanding how engines work.
And what this all gives us is a complete toolkit for understanding energy. With these laws and quantities, we can define a system's state, track its energy with perfect accuracy, and, most importantly, predict the one-way street that energy always travels on towards more and more disorder. These aren't just abstract ideas. They are the literal blueprints for building everything from a power plant to the refrigerator in your kitchen.
See, thermodynamics isn't just some chapter in a dusty textbook. It's happening right now, all around you. It's the reason your ice melts, the reason your car moves, and maybe even the reason time itself seems to march forward. So the real question isn't if you'll see these laws in action today, but where will you notice them first?